If you read Scientific American, as I do, it's not too long before you'll run across articles on quantum computing. For example, this one is entitled, How to Connect a Quantum Computer. And within such articles, you'll find illustrations of quantum superposition and entanglement and other advanced quantum concepts. In this video, I would like to talk a little bit about quantum computers from the perspective of a software engineer. And specifically, I'd like to make the point that an advanced understanding of quantum physics is not really needed in order to understand a quantum computer. So before we can understand a quantum computer, we really need to understand a classical computer and how they operate. So let me just go through the basics of a classical computer. So to get started here, let me just get a classical computer. I'm going to move this Chromebook out of the way, bring in a classical computer. So here we have a classical computer. So as you can see, the way that a classical computer is formulated is you have, on one side you have input, and on the other side you have output, and inside you have a mysterious kind of black box. So we'll take some input. So here we have 15, and we'll feed that into the input. There we go. And we'll see if we get some output. And voila, there we go. So you can see that it came up with the correct answer of 3 and 5, and indeed 3 and 5 are the prime factors of 15. So what is actually inside a classical computer? Well, let's take a look. Let's see, we have a 1 bit, and we have a 0 bit, and we have an AND gate, and we have a NOT gate. So that's some of the basics that are inside a classical computer. Well, what about a quantum computer? Well, let's see. We'll get a quantum computer here. We'll get one around there. Ah, there you go. The quantum computer looks a lot like a classical computer as well. It also has an input and an output. And let's see if it works in a similar fashion. Well, we'll take our 15 here, and we'll feed it into the input. And wait for it to do its calculations. And voila! We got 3 and 5 on the output of the quantum computer as well, factoring that number. Well, what's inside a quantum computer? Well, let's take a look. Well, look at that. We have a bit. Well, it's a little bit different than your regular bit. It has a few other symbols there because it's a quantum bit, also known as a qubit. So that's a 0, 1. And here is a 1 qubit. And lo and behold, we look further and you see there are gates inside there as well. There's an AND gate. And there is a NOT gate. I know it's a little bit of a silly example, but I hope to illustrate that the way you approach a classical computer and a quantum computer from a software engineering perspective is not all that different, although you're going to wind up dealing with some of the weirdness of the quantum mechanical world. But it's in that there's some special features that make quantum computers able to solve problems that currently classical computers can't touch. It makes that field so exciting. So hang on through the rest of this video. We're going to go through this ride on quantum computers. As soon as you do a little bit of research on quantum computers, you soon discover that they are difficult to build and difficult to program. So it raises the question of, why do we want to do this at all? Well, the answer has to do with the ability of a quantum computer to solve exponential problems. Algorithms that scale exponentially are notoriously difficult on classical computers. You saw the example of factoring 15 back into 3 and 5. Well, if you scale that up into larger and larger numbers composed of 2 prime integers, it's extremely difficult to do that work. The other thing about how difficult they are is you saw me reach into the quantum computer, but if it were a real system, some of these systems are so cold that even these guys here would not be sufficient. IBM's Q system, for example, is just a few degrees above absolute zero, colder than outer space. We can illustrate the power of being able to search problems in a different way than linearly with 4 playing cards. And this has been done before. So here we have 4 playing cards. You can see that we have 3 aces and a queen. So let's say that we took these cards and we shuffled them, and then we asked ourselves the question, could we find the queen in the set of cards? So let's set the cards down and ask ourselves, where is the queen? Well, how about here? Nope, that's ace of diamonds. So that's not it. How about this one? Nope, that's also an ace. How about this one? No, another ace. How about this one? Well, of course, that's going to be our queen sitting right there. So if you were to do this experiment again and again, you'd find that on average, it would take about 2.5 times. You'd have to look through the cards before you would find the queen. Obviously, more cards, the longer it would take each search. So now, what about a quantum computer? Let's hand the same problem off to a quantum computer. Let's just say that we'll shuffle up these cards again and we'll get the quantum computer to answer that question. So let's put the cards out, and then we just ask the quantum computer, where is the queen? Boom, right there. That's where it is. So that was just a lucky shot. So let's just shuffle them up again, and we'll ask the quantum computer again where the queen is. So we'll put them down again. And where is the queen? Quantum computer say, oh, it's right there. Boom. And there's something really kind of fantastic kind of going on. If we think about it, the classical computer is flipping over cards one at a time and looking at them. The quantum computer, though, somehow knows the card. Well, the answer is that even when these cards are down like that, the actual atoms and molecules that make up that queen, the paint and so forth, actually contains information about that card. In quantum computing, you actually can ask the system, essentially the qubits, just to reveal itself. So it'd be like asking who has December 13th as a birthday in a crowd of 100 people, and going around asking each one individually, as opposed to being able to yell it out to the crowd and that person just raises their hand. In a quantum system, the information in the system can be teased out of it. It can simply reveal itself, and that is what makes it gives it the ability to solve problems so much faster, provided, of course, we can program these systems, which is what I want to get to next. Although we're having a bit of fun looking at quantum computers and trying to understand how they work, I don't want to give you the impression that it's trivial. It is a difficult subject, and I also want to make sure that you understand that although I'm doing research on quantum computers, I can't program a quantum computer, not yet. But I have done a bit of research to produce this video, and I'm having some fun learning about the system. The basics of a quantum computer, the most fundamental thing that you're going to need to understand is the qubit, what it is and how it operates and how it differentiates itself from regular bits inside a classical computer. A regular bit in a classical computer is a pretty simple beast. It's a 1 or a 0. String them together to form larger numbers. They're very discrete things. You set them, they stay set. You manipulate them in discrete ways, and they work. Qubits are a little bit different than that. So let's take a look. So here's the problem. You do a little bit of research on quantum computers, and for example, I read a paper on the use of linear optics to do quantum information processing. It was a paper in Nature, and you run across equations like this. And I don't know about you, but for me, this is a challenge, even though I've passed calculus. You can see the 0 and the 1 qubit sort of sitting there, but then you sort of see these coefficients, this Greek characters alpha and beta. And then you see the sort of parenthetical expression. These little vertical bars indicate absolute value, and then they're squaring it and equal 1. What does all of that actually mean? That's a challenge. Well, the model that I've come up with so far, my understanding, that seems to hold up to all the research that I've seen so far, relates to a simple XY graph. And you know how an XY graph goes. There's where the X and the Y cross, that's the origin sitting at 0, 0. And then you go up the Y graph that way and across the X graph that way. But in the case of qubits, it only goes up to 1 on either side. It goes all the way from 0 to 1 and from 0 to 1 in that direction. Doesn't go beyond that. And if you had a qubit value that went all the way up the y-axis and none way down the x-axis, well, it would have a value of 1. Conversely, if you went all the way down the x-axis, no way up the y-axis, you have a value of 0. So the way that I tend to think of qubits is I think of them as floating around in this space. They are 0 and 1 in superposition, as they say, while you're not looking at them. As soon as you measure a qubit, it then falls into either its 1 or 0 value. I'll illustrate that you can come to terms with some of these equations now in regards to the manipulation of qubits, or gates, in the next segment. The paper in Nature I referred to earlier that was about linear optics and quantum information processing had the equation that we unpacked last time. Of course, that equation talked about what a qubit is, gave it a definition, showed how it was constrained to a 1 or a 0. Now, there was another section of that paper that talked about another fundamental aspect of a quantum computer, that is gates. Yeah, qubits, you need some way to manipulate them. You need AND gates, NOT gates, for example. So let's try that again. Let's try and unpack one of the equations that's in that paper. And here it is. So one of the things that happens with these sort of equations is you'll notice some of the Greek letters that appear there. And I don't know what it is with the obsession with the Greek letters, and I'm not really that good at it myself, but there's a phi sitting right there. There's an I, which is standing for imaginary numbers, and then there is a sigma, and then there's a subscript you can see with 2. As a software engineer, one thing I did recognize was the exp function, which computes the base E of an input value. So we need to look that up and sort of remind ourselves of how that particular function works. So what we do is we take out our handy-dandy Thomas's calculus early transcendentals, and we take a look at, well, what is E? How does that thing work again? And you can see that it is the natural exponential function. And these little graphs, I think, so nicely illustrate what that special E number is. We can see one graph of y equals 2 to the x. Over on the other side, we see y equals 3 to the x. And we see here where y equals e to the x. And you'll notice that the slope of the tangent line is exactly 1. That's what that E number happens to be. And you can see the actual value for it, 2.718. E as a number is basically as important in calculations as pi is to a number. And since our world is three-dimensional and these graphs are two-dimensional, these numbers, it turns out, wind up representing things in the real world and wind up in calculations. Knowing a few of those fundamentals, some of the Greek letters, we can look that up, looking up those functions, what E stands for and so forth, helps us. It gets us a little bit down the road, but not quite understanding it yet. So I turned to a friend of mine, Wolfgang Hofmeier. He has a master's in mathematics. And I asked him to help me understand this. And what he told me is that sigma sub u that you saw there, the u stands in for all the x, y, and z values. And he referred to it as the Pauli matrices. And He said that the EXP function, it can be applied to real numbers, but here it is applied to a 2 by 2 dimensional matrices of complex number coefficients. Well, the words itself that Mr. Hoffmeyer used, I've got some appreciation for what it means, but it still wasn't quite enough for, in my mind, to unpack that function, to really understand how these photons are being run through these gates in order to change their values or complement two qubits and so forth. However, it did kind of remind me about what we do as software engineers and why I think we as software engineers of classical computers can approach quantum computer programming and be successful with it. To go back to the original computer that we started out with, you'll notice that we have the computer and we have input and we have output. Inside, it's important to have a conceptual model of what's going on, how the computer actually functions. But it's also true that it doesn't have to be absolute and complete. We rarely understand the hardware that we're running on right down to the electronics that are running on the silicon. We have some appreciation for what's going on at that level, but those hardware details are not a prerequisite in order to program a computer. That's my thesis, that as a classic software engineer, you can approach quantum computing and quantum computing engineering as a bit of a black box. You can understand and appreciate that there are qubits there, that there are gates that manipulate them, and that because it's quantum mechanics, qubits can become entangled, pairs of them can become entangled, and there are special properties associated with that that allows for problems to be solved, exponentially problems, that classical computers really would have difficulty approaching.